Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's get started on our set of questions for this session. Okay, so question 1 asks, which has the larger second ionization energy, lithium or beryllium? And explain why. Okay, so let's recall what ionization energy means. This is the minimum amount of energy that is required to remove the most loosely bound electron of an atom or molecule. So first, let's look at lithium and beryllium's electron configuration. So in the case of just a neutral lithium atom, it has an electron configuration of 1s2, 2s1. So this shows that it has only 3 electrons in the atom. The first ionization energy is when you remove the first valence electron. So this gives us lithium plus once an electron is removed, and it now has a new electron configuration of just 1s2. So the question is asking for the larger second ionization energy. So as you can guess, when you have a second ionization energy, this is the removal of a second electron. So if we were to remove a second electron, it becomes lithium 2+, and its new electron configuration is 1s1. So now let's do the same thing for beryllium. So beryllium has an extra electron. So its electron configuration is 1s2, 2s2. If we were to remove one electron, this is called the first ionization energy. We get a new electron configuration of 1s2, 2s1. And then lastly, if we were to remove a second electron, this is the second ionization energy. We now have an electron configuration of 1s2. Yeah, and that's it. So if we look at both our lithium plus ion, and if we look at our beryllium plus, you'll notice that our lithium plus is already in the inner valence shell, and it's very close to the nucleus. So let me just write that down. Lithium plus has its electrons closer to the nucleus. So the closer you are to the nucleus, the harder it is to remove an electron because it is more positively charged in the nucleus. So therefore, it will be harder to remove an electron I'll put to remove an additional electron. So because it's harder to remove an additional electron, that means it will require more energy. So therefore, we can say that lithium has a larger second ionization energy. Okay, so let's look at beryllium plus. If we were to remove one electron, its electron configuration is still 1s2, 2s1. So it's still pretty easy to remove another electron. So that means it requires less energy. So the beryllium will have a lower second ionization energy compared to the lithium. So the junior tutor said, to answer this question, let's write the electron configuration of lithium and beryllium first. Lithium is 1s2, 2s1, and beryllium is 1s2, 2s2. The ionization energy of an atom or ion is the minimum energy required to remove an electron from the ground state of the isolated gaseous atom or ion. Second ionization energy, I2, is the energy needed to remove the second electron from a neutral atom. The energy needed to remove an electron from the outermost occupied shell depends on both the effective nuclear charge and the average distance of the electron from the nucleus. The farther electron from the nucleus, to less energy it would require to be removed. So the farther the electron is from the nucleus, it requires less energy to be removed. In beryllium, the first and second electron is on the second energy level, while on lithium, the first electron is on the second energy level, and the second electron is on the first energy level. The first energy level is closer to the nucleus, thus lithium would have a larger second ionization energy than beryllium. Yep, so this solution is correct. Okay, so on to question 2. HCl is a strong acid, and acetic acid is a weak acid. During a reaction with a strong base, the weak acid is forced to completely dissociate. There is no weak acid molecule left intact at the equivalence point. Since it completely dissociates, you might think the delta H of the reaction would be the same as the strong acid HCl. However, the accepted value for the delta H of reaction for acetic acid is about 1.9 kilojoules per mole less than for the hydrochloric acid. Explain why this is so. Okay, so because we know that acetic acid is a weak acid, this means that it only partially dissociates to its ions. Okay, so I'm just going to show the dissociation of acetic acid to the acetate ion plus a proton. So when reacting with a strong base, the neutralization process actually gives the energy needed for complete dissociation. So this is the reason why delta H of the reaction for a weak acid is lower. Okay, so let's see what the junior tutor said. Acetic acid is considered a weak acid. This means that it partially dissociates. For complete dissociation of the H plus atom on acetic acid, it is reacted with a strong base through titration. The neutralization process, which results to complete dissociation of the weak acid during the titration process, gives the energy needed for the complete dissociation. It supplies the energy for the weak acid to dissociate completely, hence the delta H of reaction for the weak acid is lower compared to the delta H of reaction of strong acids. Yep, so this solution is correct. On to question 3. Caffeine is the stimulant in coffee and tea and has the molecular formula C8H10N4O2. Calculate the mass percentage of each element in the substance. Give the answers to 3 significant figures. Okay, so they give us the formula for caffeine. And to answer this question, we want to assume that we have 1 mole of caffeine, and from there we can calculate the number of moles and then hence the number of grams of each of the atoms that are present in 1 molecule of caffeine. So the first step is to find all of the grams for carbon, hydrogen, nitrogen, and oxygen that are contained in 1 mole of caffeine. So I'm going to do an example calculation for the carbon. If we had 1 mole of caffeine, I can show that we have 8 moles of carbon and 1 mole of caffeine. So we can multiply this by 8 to get 8 moles of carbon. And then I'm just going to add here, assume 1 mole of caffeine. Okay, so now we know we have 8 moles of carbon. If we multiply by carbon's atomic mass, which is 12.01 grams per mole, then we know how many grams of carbon we have, which is 96.08 grams. Okay, so we can do the same thing. Let's move on to hydrogen. We know we have 10 moles of hydrogen. We're going to multiply this by hydrogen's atomic mass, which is 1.01 grams per mole, to give us 10.1 grams of hydrogen. Next, let's move on to the nitrogen. 4 moles of nitrogen and 1 mole of caffeine, multiplied by the atomic mass of nitrogen, which is 14.01 grams per mole. So we end up getting 56.04 grams of nitrogen. And then lastly, there are 2 moles of oxygen and 1 mole of caffeine. And oxygen's atomic mass is around 15.99. So if we multiply it, we end up getting 32 grams of oxygen. So if we add all these values up, we can get the total mass of 1 mole of caffeine, okay, so adding them all up, you end up getting 194.22 grams. I'm gonna put this in a box. So now that we have all these different masses, the second part of the question is just actually calculating the mass percentage. So the mass percent is equal to the mass of your component divided by the total mass multiplied by 100. Okay, so first let's do the mass percent of carbon. The mass of carbon was 96.08. And we are going to divide by the total mass of caffeine, which is 194.22. Multiply this value by 100. Gives us a percentage of 49.47%. Let's do the same thing for hydrogen. 10.1 grams divided by 194.22 grams times 100 gives us a percentage of 5.20%. For nitrogen, we had 56.04 grams divided by 194.22 times 100 gives 28.85 grams, or percent, sorry. And then lastly, the mass percentage of oxygen is equal to 32 grams divided by 194.22 times 100 is equal to 16.48%. Okay, so you can double check your answer, and if you add up all the different percentages, you should get 100%. So let's see what the junior tutor said. First thing we have to do is to assume the total number of moles of the compound. For this problem, we are going to assume that there is 1 mole of caffeine. Okay, so they showed how they got 8 moles of carbon, 10 moles of hydrogen, 4 moles of nitrogen, 2 moles of oxygen. We then have to convert these number of moles into their respective masses using their atomic masses. So they showed the multiplication of their atomic masses to get 96 grams carbon, 10 grams hydrogen, 56 grams nitrogen, 32 grams oxygen. Getting the total mass of 1 mole of caffeine, we have 194 grams. And then getting the mass percentages of each component, the mass of the component divided by total mass of compound times 100 gives us the percent mass of the component. So for carbon, 96 divided by 194 times 100 gave 49.485%. For hydrogen, around 5.155, nitrogen 28.866, and oxygen 16.495. Yep, so pretty much the same as what I got as well. So this solution is correct. Okay, so on to question 4. How do you calculate a Ka value from pKa? So a Ka is actually the acid dissociation constant. And it's different depending on the type of acid you had or type of acid that you have, which also depends on the temperature that the acid is in. So it depends on a lot of different factors. But basically, the acid dissociation constant is a quantitative measure of the acid strength. So the higher your Ka value, the stronger the acid. Okay, so to calculate a K value from pKa, let's recall the formula to calculate for pKa, which is the negative log of your Ka value. So if we are given pKa and we want to solve for the Ka value, let's recall that when we have a log, it means log of base 10. So we just need to do 10 to the power of negative pKa, and this will give us our Ka value. So the junior tutor said, remember that the formula for pKa and Ka is expressed in pKa is equal to, I think they just forgot the negative sign, negative log Ka. Expressing these logarithms in an exponential form is 10 to the power of negative pKa is equal to Ka. Remember the law from exponential to logarithmic in math, that is log base A, B is equal to C. So they showed that B is equal to A to the power of C. Yep, so this solution is correct. And then I'll just put in brackets just in case that was just a typo. pKa is equal to negative log Ka. Okay, so question 5. What is shorthand notation? So shorthand notation is used for electron configuration. So basically, it uses the noble gas of the previous row. So it makes more sense when we do an example. So let's have an example using bromine. So I'll pull up a periodic table showing all the s, p, d, and f orbitals. And how we can find the electron configuration of bromine. Okay, so here's the periodic table, and you can see that it has different sections. So this is the S block in the light blue. In the middle here with the transition metals, this is the D block. And the P block is this orange. And the last two rows are the F block. So if we were to write the long form for bromine, then its electron configuration starting at the hydrogen is 1s2, 2s2, 2p6, and then moving on to the third row, we have 3s2, 3p6, and then to the next row we have 4s2, and then when we get to the D block, it's going to be the row minus 1. So we go back to 3, and then it's D10. And then bromine is right here, atomic number 35. So we just need to count going up to the bromine. 1, 2, 3, 4, 5. 4p5. So you can see how kind of tedious and how long that kind of takes to write the long form for the electron configuration of bromine. And it gets even harder if you were to go to elements in like the F block, or if you were to do any of the elements in the 7th row. So that's why we can also use shorthand notation. So like I said, it uses the noble gas of the previous row to just kind of show where you can start from, since the noble gas is pretty much the same electron configuration as the first bit. So it's this whole thing. So in the case of bromine, the noble gas that came before it is argon. So we can write argon in square brackets and then just go on to the next row and continue writing just 4s2, 3d10, 4p5. So you'll notice that this whole part is just the same electron configuration as argon. So that's why we can just use the shorthand notation, and it makes everything so much more faster. So the junior tutor said, a shorthand notation is a representation of electron configuration that uses the noble gas of the previous line, since all the orbitals of noble gases are completely filled. Then the orbitals are filled starting from the row the element is in. Okay, so for example, the electron configuration of chlorine, the long form is 1s2, 2s2, 2p6, 3s2, 3p5, and the shorthand notation, so above chlorine is just the neon, 3s2, 3s2, and 3p5. Yep, so this solution is correct. Question 6. How does the pH of the solution on the right compare with that of the solution on the left? The Kb value of NH3 is 1.8 times 10 to the negative 5. And then they just give us different options. Both of these solutions are equally acidic. Solution on the right is neutral. Solution on the right is more basic. Both of these solutions are equally basic, or the solution on the right is acidic relative to the solution on the left. Okay, so this is a multi-step question because we are given two different solutions. One of them is a strong base, which is sodium hydroxide, and one of them is a weak base, which is just ammonium. So for step 1, let's just find the pH of the strong base first. The pH of NaOH. So if we were to write down the dissociation of NaOH into its ions, it completely dissociates to Na plus and OH minus, and everything is at a 1-to-1 ratio. So since the concentration of NaOH is given, it's equal to 0.0001 molar. This is the same concentration of our hydroxide ion, which is OH minus. So it helps to know the concentration of your OH minus ion because it will help us find the concentration of H3O plus, which helps us find the concentration of pH. So let's recall that Kw is equal to the concentration of H3O plus times the concentration of OH minus. So the value of Kw is the same. it is just 1.0 times 10 to the negative 14. And we are looking for the concentration of H3O plus. And we know the concentration of hydroxide, which is 0.0001 moles per liter. So then we can just solve for the concentration of H3O plus, which is just 1 times 10 to the negative 10. Okay, so now over here we can find the pH, which is equal to the negative log of H3O plus and in the previous step we found it was 1 times 10 to the negative 10. So its pH is just 10. And then this is for the NaOH solution, which is on the left. So now step 2 is just to find the pH of our weak acid NH3. Or weak base, sorry. Weak base. So weak bases only partially dissociate into their ions. So I'm going to show its dissociation equation. So in water, it dissociates to OH minus plus NH4 plus. So we can construct an ice table to help us solve for the concentration of OH minus. So we know the initial concentration of NH3 is 2.5, and the initial concentrations of both of our products is just 0. The change is plus X for the reactant. Oh, sorry. It's minus X for the reactant and plus X for both of our products. And then at equilibrium, the concentration of NH3 is 2.5 minus X, and the concentrations of our products is just equal to X. So first we can write the Kb expression, which is just equal to the concentration of NH4 plus times the concentration of OH minus divided by the concentration of NH3. They gave us the Kb value, which is 1.8 times 10 to the negative 5. And then if we sub in what we found in our ice tables, we get x squared divided by 2.5 minus x. So from here, we can simplify this equation to get it in a quadratic formula form. So putting everything on the same line, we get x squared plus 1.8 times 10 to the negative 5x minus 4.5 times 10 to the negative 5 is equal to 0. So at this point, since we have a quadratic formula, we can plug it into the quadratic equation, or you can just use an online calculator to solve for your x value. And we always want to get the positive value because there's no such thing as like a negative concentration. So the positive x value is 6.7 times 10 to the negative 3. Do this in a different color. Okay, so now that we have our x value, this is also the same as the concentration of our OH minus ion. So again, let's recall that Kw is equal to the concentration of H3O plus times the concentration of OH minus. Kw is equal to 1.0 times 10 to the negative 4. And then we just sub in 6.7 times 10 to the negative 3 as our concentration of OH. And we get a concentration of H3O plus that's equal to 1.49 times 10 to the negative 12. So finally, we can sub this value in our pH equation. And we get a final pH of 11.83. And this is for NH3. Okay, so now let's look at both of our pHs. And we can see that solution on the right is more basic. So that tells us that it is option C. The solution on the right is basic relative to the solution on the left. Okay, so it's a very long question. Everything somehow fit on one page. The junior tutor said to compare the pH of the solution, we need to first calculate for the pH of the solution. Let's start with the easier of the two, NaOH. Since sodium hydroxide is a strong base, it will completely dissociate into sodium plus and OH minus. Then we can use the self-ionization of water to get the concentration of H3O plus ions. So Kw is equal to the concentration of H3O plus times the concentration of OH minus. So they got 1 times 10 to the negative 10, and they got a pH of 10. Then we need to calculate for the pH of NH3. To do this, we need to calculate for the concentration of H3O plus, and we need to use the ice table. Okay, so they did the same work. They plugged in their Kb value as 1.8 times 10 to the negative 5 and got a quadratic equation, x squared plus 1.8 times 10 to the negative 5. There should be an x here, minus 4.5 times 10 to the negative 5. Okay, so they show their work plugging everything into a quadratic formula, and you pick the positive root. Since we want to obtain the concentration of OH minus, which is 6.7 times 10 to the negative 3. And then they subbed that in to the Kw expression and got a concentration of 1.49 times 10 to the negative 12. for H3O plus, and then they plugged it into the pH equation to get 11.826. So the solution of NH3 is relatively more basic, therefore the answer is C. Yep, so this solution is correct. Okay, so question 7. The boiling point of liquid hydrogen is 20.3 Kelvin at atmospheric pressure. What is this temperature on the Celsius scale and the Fahrenheit scale? Okay, so first we need to do Kelvin to degrees Celsius. And before I do the example, I'll just do like a general expression on how to calculate for degrees Celsius from Kelvin. And all you have to do is minus your Kelvin value by 273.15. And then this will give you a value in degrees Celsius. This kind of underscore just shows how you just plug a value in there. And then let's do it for our question. So 20.3 Kelvin minus 273.15 gives us a value of negative 252.85 degrees Celsius. Okay, so that's A. And now for B, we need to see this in the Fahrenheit scale. So let's do degrees Celsius to degrees Fahrenheit. So again, to get a value in degrees Fahrenheit, this is equal to a value in degrees Celsius multiplied by 9 over 5 plus 32. Okay, so let's try to solve for this. So we know the value is negative 252.85 degrees Celsius. We need to multiply this by 9 over 5 and then add 32. And then we end up getting negative 423.13 degrees Fahrenheit. Okay, so the junior tutor said, from Kelvin to Celsius, you subtract 273.15, and they got minus 252.85 degrees Celsius. Then for part B, convert the temperature solved at letter A to Fahrenheit using the formula. Degrees Fahrenheit is equal to degrees Celsius times 9 over 5 plus 32. So negative 252.85 times 9 over 5 plus 32 is equal to negative 423.15. Yeah, so pretty much the same thing I got as well. So this solution is correct. Okay, so question 8. Give the actual ground state electron configuration for copper using the complete form. So to find the electron configuration, we first need to divide the table into different sections. So this light blue section is denoted as the S block. This green section is the P block. And the middle transition metals are the D block. And the last two rows is the F block. So to find the electron configuration, we start at hydrogen, and then we just move from left to right down the periodic table until we get to our desired element. So in this case, it is copper, which is found right here, atomic number 29. Okay, so as we move down the periodic table, we want to first write down our row number, and then we want to write the block letter, so whether or not it's S, P, D, or F. But once we get to the D block, it's going to be the row number -1, and then when we get to the F block, it's the row number -2. So this will make more sense once I start showing how to find the electron configuration of copper. So let's start off at hydrogen. Its row number is 1, its block number is S, and then in the 1s orbital, there's hydrogen and helium, so there's 2. So you write 1s2. And then you do the same thing going down to the next row, 2s2. And then moving over, we're in the 2p. And then the number of elements there is 6. And then to the next row, 3s2. Oops. And then 3p6. And then the next row down, 4s2. And then counting up to the copper, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 3d9. So at this point, when you get to your electron configuration, it's typically done if it's not like a transition metal, but it gets a little more not complicated, but you just need to think about a few things about which orbitals are more stable compared to other orbitals. So for example, filled D10 orbitals are more stable than when they're partially filled. So now that we know this, we see that our electron configuration ends in 3d9. So what happens is that one of the electrons in the 4s2 orbital is actually moved up to 3d10 to form 3d10. So therefore we can rewrite the electron configuration so that it is 4s1 and then 3d10. Okay, so let's see what the junior tutor said. Writing ground state electron configuration follows the Aufbau principle. The Aufbau principle states that electrons must fill the lowest energy shells first, and the electron configuration chart shown below shows Aufbau's principle, and this chart will help us determine how to properly assign electrons of an element to their proper energy shells. Electron configurations are written using the principal quantum number n, followed by the orbital s, p, d, or f, with the total number of electrons written as a subscript. So this is another method that some people like to do. So this helps you get the order of the electron configuration. So if you write all of the s values in one column, all the p in one column, and then all the d orbitals in one column and the f, and then you kind of just move like diagonally like this, then you get 1s, 2s, and then 2p, 3s, 3p, 4s, 3d, 4p, 5s. So that's another way people do it as well. So before we can use the electron configuration chart, let's determine the number of electrons copper has. So there's 29 in its ground state. So when we'll write the configuration, we'll put all 29 electrons in orbitals around the nucleus of the copper atom. Okay, so since s orbitals can only hold 2 electrons, the next 2 electrons for copper go to the 2s. So they do it like step by step. P orbital can hold 6, so they wrote it all down. The d orbital can hold 10. And then they mentioned that our expected electron configuration for copper would then be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. They also wrote half-filled d5 and filled d10 orbitals provide extra stability to the atom. This makes copper an exception to Aufbau's principle. We adjust to this by making one of the 4s2 electrons jump to 3d9. This gives us the correct configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Yep, so this solution is correct. I think we have time for one more question. So question 9, how do you find the number of protons, neutrons, and electrons given the atomic number and the mass number? So the atomic number on a periodic table, which can also be symbolized as Z, this gives us the number of protons. And the mass number on a periodic table is equal to the number of protons plus the number of neutrons. Okay, so that's how we solve for protons and neutrons. And lastly, if we have a neutral atom, so if it has no charge, then the number of protons of the atom is equal to the number of electrons. Okay, so that is all 3. So let's write out an example. So for example, let's say we had chlorine. It has an atomic number equal to 17, and it has a mass number equal to 35. So the number of protons is equal to 17, which is also equal to the number of electrons, And for the number of neutrons, it is just 35 minus 17, which is 18. Okay, so the junior tutor said the atomic number Z is the same as the number of protons of an element. So if the atomic number is 5, the element has 5 protons. The charge of the substance must equal the sum of the protons and electrons. We simplify charge of a proton is +1, and the charge of an electron is -1. So in neutral substances, the number of protons and electrons are equal. For example, if we have a neutral atom with 3 protons, it must also have 3 electrons. Lastly, the mass number A is the sum of the number of protons and neutrons. To get the number of neutrons, we subtract the number of protons from the mass number. If an atom has an atomic number of 5 and a mass number of 8, the number of neutrons is 8 minus 5, which is 3. Yep, so this solution is correct. All right. So if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And always, if you enjoyed today's video, go ahead and give it a thumbs up and a comment. And you can also share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.